hopefully early in the weekend. Okay? And I guess I don't know when you have to turn it in. I guess in a week or two. Do you know the rules? No. Okay. Very good.
Will you send them by email?
Yeah. So I had a list of emails from the first day, and I gave it to him. Was your email there?
Yeah.
If it was, okay. So then you have the paper, right?
Yeah, sure. I sent an email in which I said what time my office hours are going to be. So if you haven't received it, then
yeah.
you should let me know that you're not on my mailing list.
My question is, will the homework be sent by email?
Yes.
Okay.
How else otherwise? Okay, no, by email, yeah, sure. Okay, so before we start, any questions about yesterday's in this crazy way of doing things? Yesterday's lecture? No? Okay, so what do I want to do today? So today let me just recap a little bit. So what we've been doing so far is essentially to study what the constraints of conformal symmetry are on field theories. And we have assumed nilly-willy that conformal symmetry is an exact symmetry of the field theory. Okay? So what I want to discuss here is the subject of conformal. So there are several names for this. While or trace anomalies. Okay. And there are several reasons to do this. One is just that the existence of anomalies is foundational to all quantum field theory. Okay, it's not that we only have anomalies for wild symmetry. We also have anomalies for all kinds of other symmetries, both global and gauge, and understanding how and why anomalies arise in quantum field theory is at the heart of what quantum field theory is all about. Okay? So today I will discuss it in the context of the wild anomaly. And what we will see is that by using very simple physical principles, we will be able to discern what kind of anomalies conformal field theories can have in the various dimensions. So that's going to be one of the points. So this is just basic to quantum field theory. And then I'll define more carefully what do I mean by this word of anomaly. And the second point that will be very useful and that will tie up to discussions we had earlier in the week is the following. So remember that in this picture that we have of field theory as an RG flow from an ultraviolet theory to an infrared theory. A priori, since these RG flows, even if the theory here was weakly coupled, the theory in the infrared can be arbitrarily strongly coupled. It's hard to know what kind of theories you can get in the infrared. So one of the things that anomalies, so certain quantities that will appear in the study of anomalies that will play a crucial role in establishing basic, there are certain theorems that we will be able to prove just using abstract arguments that will allow us to tell you that there is a certain quantity that is monotonic. So it means that, let's call it CUV. There's a monotonic quantity that at the ultraviolet fixed point is a quantity called C that will appear in the conformal anomaly, that in the infrared reduces to the quantity that appears in the conformal anomaly of the infrared theory, and that has the property that's monotonic. So that for an arbitrary RG flow of a unitary quantum field theory, the central charge of the ultraviolet theory decreases. So CUV always decreases, this quantity always decreases under renormalization group flow. So this in particular gives very strong selection rules, because if you can compute the central charge of two CFTs, you can discern whether these two theories can be related, cannot be related by an RG flow. And also tells you something very deep about the RG flow. It tells you that it's irreversible. So if I can have a theory A that flows to theory B, there is no way that theory B can flow back to theory A, okay? Because that would violate this inequality. Okay?
So is it a strict inequality?
It is a strict inequality, yes.
Because
Yeah, and you
it's
can,
trivial on the fixed point, it clearly violates strict inequality.
sorry? No, so,
Just the RG flow on a fixed point clearly.
no, so what can happen is that if you have a conformal field theory that has a line of fixed points, you have a conformal manifold, what's called a conformal manifold. Then, of course, one thing you can prove, and it's not very hard to prove, is that this quantity is constant along that manifold of marginal deformations. But if you really have a real flow, C will decrease. And here what we will see is that there's a very important difference between anomalies in even and odd dimensions. We will see a very simple reason why. And I hope that I also have time to say that nevertheless, there is a quantity that is kind of measures, isolates this quantity in a conformal field theory, which is the sphere partition function that allows us, even in odd dimensions where there's not going to be conformal anomalies, to at least postulate a certain quantity that is also monotonic under RG flow. And this, again, will give us non-perturbative selection rules for what kind of flows can exist just using basic principles of field theory like unitarity, Lorentz invariant, diffeomorphism invariant, and so on. OK, so that's kind of the goal. Let's see how far I get. So what I want to do is set up the problem. I'm not going to erase that. What I want to do is, for the purposes of studying the conformal anomaly, is to consider coupling your arbitrary conformal field theory to a curved background. Which has a fiducial metric G. Okay? And I want to consider something that we have already considered, which is the generating functional of correlation functions for the stress energy tensor. Okay? So this quantity that we have already discussed before captures connected correlators of the stress tensor. Okay? Now here, for simplicity, I could have equally well done it. I have just turned off the sources for all other operators in the CFT. Remember that I could have added some source JA for an arbitrary operator OA in the CFT, but to make life simple, let's just focus that we're looking at the partition function when the theory is just coupled to a background metric. You could couple it to other background fields. Okay? Now, the statement of Weil invariance as a symmetry is the statement that this object, or let me focus always on this guy, which is the one that generates the more interesting correlators, which are the connected correlators. The statement of Weil invariance is the statement that if I make a Weil transformation, arbitrary Weil transformation, this generating functional is invariant. Okay? Good. So now, let's discuss in this context why there can be an issue with this statement quantum mechanically. Okay, so I have to tell you some things about field theory. Of course, just qualitative things. I cannot get into the details of that. I think some of the things you probably have seen in QFT1. There are just a few things I want to say. Is that in quantum field theory, in general, not only for conformal field theories, generating functionals of this type have ultraviolet divergences that comes from very short distance fluctuations that are omnipresent in quantum field theory. Okay? And the fact that we have ultraviolet divergences, it means that we have to normalize. And the physical way to think about what this really means is that this normalization procedure is, what it does essentially is parameterize our ignorance about what happens at extremely short distances. There could be quantum gravity there, there could be elephant, we don't know. In terms of the redefinition of the coupling constants and fields in our theory, okay? So this is a way of parameterizing our ignorance. And the point is that this procedure gives rise to some definite predictions about the low energy physics that's predicted by that particular field theory. Okay? Good. So in practice, the way we do it is that we have to regulate these divergences and subtract them. And the way we regulate divergences in a physical way, what we have to do is take the theory and do some massive deformation or add some heavy degrees of freedom in the ultraviolet. So you have to do some kind of massive deformation. But in some sense, what you're doing is introducing a scale, which is the ultraviolet scale, where you declare, okay, I don't know what I'm talking about. Above this scale, I don't know what's happening. And this introduces some scale, and we're going to study the theory in that regulated theory, and this you can think of it as a massive deformation. Okay. So now, once you're done with this procedure, you have to go back and ask, okay, so I have regulated my divergences, I renormalized them away. If I had original classical symmetry, is the symmetry still there after I'm done with this process? Okay. So that's the whole subject of anomalies. Okay. Another way of saying it, maybe more formal, is that even though the classical action, if you want to think in that language, can be symmetric under certain symmetry, the measure of integration, the functional integral, this infinite dimensional integral, cannot have that symmetry. That gives you an anomaly. Usually the anomaly can be thought of as arising from the measure of integration. Okay. So if we have a classical symmetry, by Noether's theorem, implies that there is a conserved current of this type, okay? So now what we're asking is this symmetry preserved by regularization, okay? And that's what we're trying to discuss, okay? So what we call a theory anomalous symmetry. No, the theory is not anomalous, the symmetry is anomalous. Is if due to wild quantum fluctuations, we're not able to preserve this symmetry quantum mechanically. Okay? So this means that A mu, J mu is no longer 0, and it's proportional to some quantum effect that I'll call it h bar. Okay? So it's no longer 0, but it's proportional to h bar. So this is something you can study for all symmetries that you know. But for example, for flavor symmetries in gauge theories, you can even also discuss it for discrete symmetries. But of course, we don't have a conserved current associated to discrete symmetry. But you can also ask about that. Okay? Here, what we're interested in is the following. So here, while invariance implies two things. Implies that P mu mu equals 0. Okay, that's the basic prediction of while invariance. So now what we're trying to study is whether T mu mu is 0 or non-zero in a quantum theory.
So they're doing it as an operator?
Sorry?
Doing it here.
As an operator? Yeah, as an operator equation. So this would be an equation that would be valid at inserted in the path integral. Perhaps, so typically the way to think about it is that think of this equation that's valid everywhere, except perhaps if it collides with some other operator. Then you can have a contact term.
So,
yes?
I mean, if I really took that and tried to find this definition, the statement exactly would be that G mu nu contracted with the mean of P mu nu.
Yes, but
it's not 0. I mean, it's not. I mean, in this form it's misleading, but that's what you can have in all generality, right? Because you can have G mu nu contracted with the mean of the stress.
Yeah, but G here is not it's not.
Yeah, it's a fiducial metric. But
it's a background metric,
yeah.
So.
So I mean, that's what you take the trace of.
Yes. Okay. So are you saying that by this, of course, I mean T mu nu, G mu nu?
Right, but since it's an operator equation, you
yeah. So the operator equation, I don't have to write that. That's the whole point. An operator equation means that it's
yeah.
If you prefer to put a expectation value, that's fine. I want to think more of as an operator equation that.
Yeah, it's just in the context context of QFTs, when you're used to seeing void identities, then this is always written using the context of usual QFTs.
Yeah, but in QFTs you can also write equations like that. I mean,
G is close to a fiducial metric, right?
sorry?
G is close to fiducial, the background metric, right?
G is the background metric.
So even in flat space, you can still have trace being 0, but that's very being anomalous.
Yes. Yes. No, but
it's
okay.
not anomalous near the flat metric. The trace is not 0 near the flat metric.
So
that's the thing. So you've also promoted G to something.
Yes.
That's. I mean, if you write it as an operator equation, then the cost is that you promote G, the fiducial metric, to something that's not necessarily.
no, I mean, look, so right now I'm looking at the dependence of partition function on the metric. So in flat space, when we discuss anomalies, it may happen that the anomaly vanishes. But now imagine I couple, even in flat space theory, my theory to other sources. And then you will find that, okay, if you don't know what this means, don't worry, but just to answer this question, even in flat space, you can have a violation of T mu mu equals 0. Because, for example, you have a theory that quantum mechanically has running coupling constants, but you will have is an equation and a schematic of this type. So you have logarithmic running of the coupling, you have the beta functions for your field times something like that. And this is in flat space. Even though the contribution from the curve metric vanishes. Okay.
So, but I'm talking about the other case. This definition doesn't seem to capture those cases where T mu mu is 0 in flat metric, but if you go near the flat metric,
it does. Okay, you'll see. I mean, you're jumping ahead. It captures all the cases with flat metric, non-curve metric, whatever. Just wait. You will look at that. Yeah. Okay, and notice that this equation is also going back into this language. If you think in terms of flat space, this T mu mu, remember, was the dilatation current. Okay, the statement about dilatation current conservation, right? Because the dilatation current was J mu T mu nu x nu, right? Because this is the Killing vector associated to dilatations. And therefore, conservation equation is the statement that T mu mu is 0. Okay? Good. So now we want to study just from using very simple principles. So the way you usually found this in textbook is by doing horrible computations of scalar fields coupled to a background metric, doing hit kernel, and that's not the way to think about it. I'll give you a way to think about it that will lead to immediate results in all dimensions. Okay. Okay. So what we want to do is compute essentially. So how do we characterize that we have a conformal anomaly? Well, this will be captured by the variation under an infinitesimal Weyl transformation of this object. Okay, so now what I'm going to do is just do an infinitesimal transformation. And ask whether this object is invariant. Okay, this is the right-hand side is by definition what's called the anomaly. Okay, so now what are the rules of what I can do here? So we're going to try to parameterize what is, just using general principles, what is the most general thing that can appear here on the right-hand side. Okay? The first statement is that since anomaly arises from very short distance physics, essentially what you're doing is integrating out very massive excitations. This means that whatever you're going to get has to be a local functional of the field. Okay? Because if you integrate massive particles, what this gives rise is to local terms in the effective action. One way of saying it is that if you integrate out a very massive particles, you can expand in momenta, and you just get a power series in momenta, which is just a derivative expansion, and each term is local. Notice that this is not true if you have if you integrate out a massless particle. You can have non-local behavior, but since we are adding very high energy degrees of freedom, then we're going to get a local. So we're going to, what are the rules? So we're going to get, we have to impose that it's going to be a local functional of the metric. And we're going to impose that it's deep invariant. And And the reason we can do that is that we know that there are regulators who can regulate these divergences in a diff invariant way. Okay? So then we're going to now study this object. So we're going to have integral over space-time square root of g times a of sigma of g mu naught. And this is the anomaly that we're going to study. Okay? Several things that this guy has to obey. So it has to obey that it's linear in sigma, right? Because I'm doing an infinitesimal transformation, therefore the variation has to be proportional to the infinitesimal parameter. 2, now we're doing dimensional analysis. This guy has to be the most general diff invariant operator. I use the word operator even though the background field is a background. But anyway, this is a standard language when you do this kind of analysis in quantum field theory. The most general diff invariant operator of dimension equals to d. The reason is that there is no scale in the problem, and this guy has to have dimension d. Okay? And then the other important constraint is that the anomaly, if you wish, has to represent the wild symmetry appropriately. Okay? What do I mean by that? I mean that if I make two consecutive transformations, so obviously wild transformations form an algebra. In fact, in this case, it's just an abelian algebra. So if I do, it shouldn't matter if I do a sigma 1, sigma 2 transformation, or then first sigma 1 and then sigma 2. Okay? So in formulas, what this means is that you have to, since wild transformations commute, it's an abelian symmetry. This equation will be slightly modified, but in an obvious way for non-abelian symmetries. Let me write it in full glory once. Minus my definition. Do I have no? Okay, my definition. The square root g is hidden here. It doesn't matter. Okay. I'll try to be consistent. It has to be 0. Okay. This is just a statement that the anomaly represents the commutation relations of the wild transformation. If you had a non-abelian symmetry, so imagine you do delta 1, delta 2, and that symmetry the commutator is non-zero. You have delta 3. Then here you would have to get delta 3 of the guy. Okay? But no, I'm not going to write it, not to confuse it, but it's just a pretty obvious condition, but it's an extremely important one, and this is called the Wess-Zumino consistency condition. Okay? And we will see that this will reduce the space of possible terms that we're allowed to write here. Okay? So these are not allowed because they don't represent the wild anomaly properly. Okay? Okay, so where do we start? We start in 2 dimensions. And then immediately try to get a feeling for what's going on. So let's study this problem that will have lots of physics in it, just with this very simple rule. So let's study 2 dimensions. So now what we have to do is write the most general functional that satisfies these properties. So can you provide candidate terms?
You mean A's?
For A's, yes. Does root G have dimension D? Dimension 2?
Oh, you mean dimension 2? No.
I mean, this is a very important requirement, okay? This is... So the balls that you have to play with are sigma, x, and g mu nu of x. And you want to construct dimension to scalars.
Could you explain once again why the operator has to be a Formosan invariant?
Yeah, so the reason it has to be is, well, so there is an assumption, but in all cases it's realized that you can regulate the theory in a diff invariant way. So since you have, it's like when we regulate divergence in flat space, you can have manifest Lorentz invariant regulators, and therefore the answer you're going to get is going to be Lorentz invariant. Likewise, for the symmetry, there are diff invariant regulators, and therefore the answer is manifestly diff invariant. But there could be a tension about having diff invariant and wall invariant at the same time, and that's exactly what we're trying to probe.
Which is scalar? Which is scalar?
Yes. Okay. So give me precisely what something that has all these properties. Okay. Forget about this one because this one we'll have to go back to it. At least these first two.
Sigma times which is scalar?
Okay, with square root of g, right? I want a scalar, so. Yeah. Okay. Something else? Okay. And the crucial point for if everyone is not following is that the dimension, of course, of R is 2. It has 2 derivatives, so it has dimension 2. Sigma is dimensionless, so this has dimension 2, and it's obviously a diffeomorphism scalar. Okay, anything else we can try to write? Okay, something you can write, but okay, I can write this. What's wrong with this? Well, what's wrong with this is that it's a total derivative, and therefore it will integrate to 0. Okay, but just keep in mind that these such tricks are allowed. So that means that what we've concluded from this trivial analysis is that what can appear on the right-hand side is this. Okay, I'm going to choose a normalization for, if I can read my handwriting. What is this? I think it's 64. R. Okay. Now what we have to check is whether this guy satisfies the Wells-Domino condition, and the reason it should be pretty. Well, is it obvious? Maybe it's not completely obvious. So the way you have to check it is now by doing a wild transformation of this quantity. So what you have to do is open a GR book and see how, for example, R transforms under a transformation like that. Okay, this will transform, right? So to R some or sigma. And then see whether this equation this relation is satisfied.
So what did the C over 64 come from?
Yeah, so this, of course, what I wrote here is just a number.
In, no, you saw that it should.
I will connect it to something that, yeah, but I have to be causal. I mean, I cannot, yeah. So I could have put some crappy number here, and then I think it's better that I already tune the number to something that is interesting, and then explain what this number is. So, okay, the thing that's important is that here there is a arbitrary thing that I can turn here. See? This is exactly the anomaly coefficient. It's a property of the theory that you have to compute. Something that, again, that's important to mention is that a priori, you could have thought that this coefficient could be position dependent, but actually, imposing the Wells-Domino condition, you prove that it's not. Okay. So what is this C? This is exactly. We'll connect it to the discussion I had at the beginning in a second. Okay. Another way of stating the anomaly is using the language of the trace anomaly. Now I can compute what T mu mu is. So I had used the word here, trace. Now from this function, I can compute what T mu mu is, right? And T mu mu now will not be 0 anymore, will be minus C over 24 pi times the rich scalar, okay? And this C, okay, so you really haven't studied in detail two-dimensional conformal field theories, but you will do it in the last week. this guy is the central charge. So remember that I said it in 2 dimensions, the conformal symmetry is infinite dimensional, and it actually admits a central extension, so it means that you can add a generator that commutes with all the other ones. And that generator is precisely this guy, the central charge. Okay? So this quantity, which appears in an anomaly, also appears in the central charge of the Virasoro algebra of the conformal field theory, of 2D conformal field theory. Now let me try to connect this C to some other things. So you could ask, is this C, first of all, and the reason I chose this normalization is that if you compute now C for the simplest case, say for a free scalar field. So even a free scalar field, even a stupid free scalar field, you would think, how can this guy have any anomaly? A free scalar field has an anomaly, conformal anomaly, and C equals 1 in this normalization. Okay. Now you can start asking, what is the incarnation of C? What's its physical incarnation? Okay. So one thing that I will not prove here, but it's not very hard for you to convince, at least I hope, to convince you that it's reasonable, is that from this equation, by taking functional derivatives with respect to the metric, which means bringing down the stress tensor, and then evaluating in flat space, this will give me correlators of the stress energy tensor in flat space. Okay. But now they will probe this C, okay? So in particular, in 2 dimensions, if I defined, now we're in flat space. You define TZ to be the ZZ component of the stress energy tensor, where Z is kind of the obvious complex combination of the coordinates. You can prove from this essentially that TZ T0 is C over 2, Z over 4. Okay? So you see that even the theory in flat space knows about the conformal anomaly. And in fact, that's by far the simplest way of computing what C is for a free scalar field. If you try to do it by coupling a scalar field to background metric, it's complicated. You have to do some heat kernel analysis. While doing it in flat space is totally elementary. You just have to compute the 2-point function of free field, essentially. Okay? So what does this C control? So C determines various important physical quantities. On the one hand, it measures the Casimir energy of the CFT, or it appears in the Casimir energy of the CFT. So you put your CFT in a finite space, so you put it on a cylinder of radius L. Then a computation shows you that the Casimir energy, which is the energy that you get from fluctuations when you're at finite volume, scales like C. Okay? It also controls the density of states at high energy in the conformal field theory. Okay? So this is obviously something that you would be interested in. You want to know, if I go to very high energies, how does the density of states behave? Okay? And the important quantity that appears in this analysis is precisely the central charge. So if you compute the entropy at very high energies, what you find is that it scales like the central charge times the square root of the energy, okay? At high energy. This is the asymptotic behavior. Okay? So these are 2 places where this quantity that seemed unphysical. What is this crap anomaly? Blah blah blah. It appears in absolutely physical quantities like these 2. Okay. And perhaps more importantly, and related to the story I was telling you here, is that C really gives you a measure of the number of degrees of freedom of the conformal field theory. Okay? And this quantity that we were looking after that would be monotonically decreasing under energy flow is precisely this C. Okay? So the quantity that will decrease is this CUB bigger than CIR. Okay? So this mysterious thing that we were looking for is an anomaly coefficient. Okay?
What is the degrees of freedom?
Sorry?
What is meant by degrees of freedom?
Yeah, so this is not used in a very precise sense, but the intuition why I use these words, well, in two-dimensions actually it's quite precise because it tells you the asymptotic density of states, right? It's controlled by C. But in higher dimensions, this is not true anymore. But the raw intuition is that when you do an energy flow from high energies to low energies, how do you do it? What you do is you integrate out heavy particles, right? And you flow to the infrared. So intuitive, what you're doing is that you're losing degrees of freedom when you go from the ultraviolet to the infrared, right? And that is in the sense in which I'm saying that. So you have, when you integrate out, you lost degrees of freedom, and now you found a quantity that has decreased along the energy flow. But in two dimensions, it's very, I mean, I'm telling you that the entropy goes with C. Okay. And the fact that this exists gives you a very strong constraint on the type of RG flows that you can have in two dimensions. In two dimensions, as you hopefully you will see, and otherwise you should force Freddy to tell you, there's an infinite number of conformal field theories that are called the minimal models. And just knowing this immediately tells you kind of a stop signs of what theories can flow to what other theories. Okay? So it's already a very strong constraint. Okay. As usual, I don't know how much I want to say about this. Now, of course, I haven't proven this to you yet. Proving this is what's called the Zamolodchikov theorem, which maybe I'll sketch. Because it's so simple and elementary and powerful that I cannot resist by show it.
That's what people call the C theorem.
Sorry?
That's what people call the C theorem.
That's what people call the C theorem, yeah. Yeah, okay.
Not sure.
I'm not sure I'm spelling Zamolodchikov even right, so.
It does have a C in it, so that's fine.
Yes. Is that how you spell Zamolodchikov?
That's how I do it.
Okay, that's
In
also
Russian, that counts.
Okay. Let's agree to that then. Okay, so how would you prove such a thing? Also notice, well, as I already said at the beginning, the fact that you have this, it tells you that you have irreversibility of RG flow. For example, you can go down the hill but not back up. This is interesting. This is interesting statement about field theories. So now the way you can prove the Zamolodchikov theorem is the following. Now you are in you're studying an RG flow from the ultraviolet to the infrared, and you're studying the most general two-point function of the stress tensor anywhere around the flow. And this is just fixed by essentially word identities like we discussed yesterday. So we look at TZZ at Z, TZZ at the origin. Where R square is ZZ bar. So notice that the powers of Z is determined by the spin of the operators on the left. So you have 4 Z's, you have 4 units of rotation in one direction. You get it here. Then you have TZZ of Z with TZZ bar. Notice that TZZ bar okay, so something I should have said is that in 2 dimensions, the trace of the stress tensor in flat space is just this ZZ bar, right? Because you only have that. So this guy is another function of the distance divided by, okay, this I'm cherry picking normalizations to make some other formulas simpler. And then I have the two-point function of the trace with itself. Okay? And now what you do is the following. You impose conservation. The fact that the stress tensor is conserved. That's just a statement of translational invariance. So you have, in complex notation, is del var, tz var, z, plus, sorry, I want to do it this way. So plus d z z bar. Okay, this imposes some relations, some equations for f, g, and h. Okay, which I'm not going to write down. They're really trivial to derive. But now, the observation that Zamorodchikov made is the following, is that if you take a particular linear combination of the functions, arbitrary functions that appear there, so f, g, and h, you can construct an object that's monotonic. Okay? So what you can define is a quantity C function, which is 2f minus g minus 38h, that if you compute the derivative with respect to the log of r squared, so it tells you how it changes scale, what you find is that equals to minus 3/4 h, okay? Where h is the guy that appears on the right-hand side of the trace of the stress energy tensor, okay? And now what you use is some spectral decomposition of the two-point function, and essentially notice that in a unitary theory, the two-point function of the same operator has to be positive, okay? So what this means is that this guy is negative, okay? So it decreases. So that means that C is a quantity that is defined everywhere along the flow, but decreases towards the infrared. And at the asymptotic endpoints of the ultraviolet and the infrared, it reduces to the central charge of UV or IR, asymptotically in the flow. And this just follows from what I computed here, right? I told you what the two-point function of a conformal field theory scales with the Virasoro central charge. Okay? And from here, we get that CUV is bigger than CIR, okay? Which is the thing that we wanted to show.
Yes, may I ask a question?
Yes?
I don't understand these two-point functions, okay? They have this form only in CFT, okay?
In what?
Only in conformal theory. I mean, if we consider, for example, RG flow between two different conformal theories, okay?
Yes?
Then probably this two-point function have this form only in the fixed points, but not in between.
No. Here I'm allowing arbitrary functions of R here, right?
Okay.
If it's conformal invariant, this H is 1, right? Okay.
It should be zero in a conformal because the TZ bar would be 0, right?
Okay, sorry.
H and G would be 0 and F would be C over 2.
Sorry, so, no, sorry, so, yeah.
What was H?
No, you're saying that C should be here.
No, I think it is correct. It's just that the specific formula assumptions take when F here is a CFT, that F is a constant.
Yeah, and this is 0.
And G and H are 0.
Yes.
These are correct in plus.
At separated points, yeah. So the statement of a conformal anomaly is that in flat space T is 0 away from other operators.
But I'm missing something here, but that statement seems to be something that you make in theory space. You're relating R squared to RG time, right? I mean,
Yes.
so how, I mean, to get a better picture. How
Yeah, so what does it mean? Sorry, this is ridiculous. I'm sorry. Okay.
So why do it? Yeah.
So flowing to the infrared means that you look at the physics at largest distances, right? So I'm just looking at how things evolve from looking here to very large distances.
Right, but then, I mean, in no other field theory could I relate.
Sorry?
No, it's just, okay.
Okay. Good. Let me move on.
Still, I don't know. I mean, this form of correlator is not the most general, okay? So how do you get it if you are not?
So, is the most, in what way is not the most general? Try to write something that you can write down consistent with.
For example, okay, z part 4 is not the same as z part 3 multiplied by z bar, okay?
Sorry.
Okay, expression, for example, general f of r squared divided by z power 4, okay? It's not the same as, say, general g of r squared divided by z cube z bar, okay?
But you're assuming rotation invariance.
Yeah, Lorentz invariance. You have to impose Lorentz invariance. That's what I was saying, that the number of indices here have to match the number of z's and z bars here. That's rotational invariance. I mean, you cannot sprinkle z and z bars as you will. I mean, it has to be consistent with Lorentz invariance.
So you get this form of elevators just from Lorentz invariance?
Yes.
Ah.
Yes. Okay, I thought I said that, but yes, this is Lorentz invariance. Yes. Okay, another just comment I want to say, because maybe you will see integrability later in the course, is that sometimes, so now in 2 dimensions you can get interesting RG flows between different conformal field theories, and sometimes, of course, in general it's very hard to solve a theory along an RG flow, but in 2 dimensions you can have integrable deformations that allow you to study in detail anywhere along the flow the theory, okay, and extrapolate continuously from the ultraviolet to the infrared. But this we really know how to do only in 2 dimensions where you have integrability. Okay, so let's go to. So you see that by looking for anomalies was fruitful. We identified some quantity that. Oh, this is perfect. That had some very physical properties, and that told us that how to characterize, at least partially, RG flow. Okay? So now we want to study a similar story in 3 dimensions. And we will see that actually in 3 dimensions, the story is completely different. Okay? So now again, we have to look at, so now I ask you, what are the allowed terms? So remember that the physical requirement was that since we're integrating short distance physics, what I have to write down is the local function of the metric and sigma that is diff invariant. So what can you write down in 3 dimensions that has dimension 3? Sorry? Sorry. What is Gimino?
So you can use out the power of 3 halves.
That's not local.
It's not local.
Yeah, okay, so you should see immediately that.
Can I do something like epsilon alpha beta gamma, the derivative of sigma times the ratio? No, that's symmetric, so you can do it.
You find one, you'll become extremely famous. But no, so you can't, because basically the basic point is that the curvature invariance. But actually, I'll show you that there was a potential candidate that fails in a very interesting way. So you can have R. This has even dimension 2, right? So whatever other things you're going to write that are going to be scalar and curvature invariance will be even dimensional. So this already tells you immediately that there can be no anomalies, no conformal anomalies. And we haven't done any hit kernel expansion or any garbage like that in odd dimensions. But now, just for fun, I'm going to tell you some term. Okay, so this, if you don't know what I'm talking about, ignore it. But otherwise, if you know what I'm talking about, I think it's illuminating. So imagine there's actually one object that you can write down in 3 dimensions that has dimension 3, that almost has the right properties. So in 3 dimensions, you can write down what's called a Chern-Simons invariant using the spin connection. Okay, so you can have something like this object appears prominently in the studies of 3-dimensional gravity, classical and quantum. Okay, so you could say, what's the problem with me writing something like that? This would be a term that has the right dimension. The reason it fails is that this guy, under the diffeomorphism, transforms into a total derivative, and therefore the whole thing is not diff invariant. Okay, so if this sigma x was not here, this would be diffeomorphism invariant. But the fact that you have an arbitrary function of sigma here tells you that this is not diff invariant. So even this term is not allowed. So this really is the conclusion of this statement. Okay? And by the way, this term exists in any dimension. So in any other dimension, you can construct a Chern-Simons term like this. Essentially, by the way you define these guys is is a 2k plus 1 form that has the property. So you can write down in 3 dimensions is this, but the basic defining property is that d of it is traced to r wedge r. Is it k times? Okay. So this shows in a very simple way that there cannot be conformal anomalies in odd dimensions. Then you can ask, is there a quantity like C in odd dimensions? So clearly this cannot have anything to do with anomalies. And we will see later, if I get to it, that there is a very unifying picture of what this quantity should be in any dimension that once you phrase it in that language, does not have to do with conformal anomalies, but that selects conformal anomalies in even dimensions and something else in odd dimensions. Okay, so we're done with the equals odd. Now let's go back to the, of course, the interesting case of d equals 4. So here now you're already professional, so you should be able to tell me all the possible terms.
So can a unitary theory flow to a non-unitary theory?
If the deformation is reflection positive, I would say no. By the way, one should not insist too much, especially in 2 dimensions, on the theory being unitary. There are many interesting CFTs that are not unitary and describe critical phenomena like the Lie edge singularity. You use the idealizing model with an imaginary magnetic field, you can get an interesting scaling behavior out there. So one should love unitary, but be open-minded that there are interesting systems that are unitary. Yeah. Okay, so let's study d equals 4. Now, what are the possible operators that can appear in A sigma?
Curvature square.
Okay, which curvature?
Riemann curvature.
Riemann curvature square.
I guess even wild.
Sorry?
Even wild curvature.
Rich's scalar square.
Rich's scalar square.
Yeah, wild curvature.
Yeah, say something simpler.
Rich's tensor squared.
Rich's tensor square. Ah, okay, all this with sigma, right, in front?
Yeah.
Yeah, okay, 6 sigma is outside. Imagine it's just sigma times some graph. Okay, what else?
Rich's scalar times the Laplacian of sigma.
Yeah, or likewise, sigma times the Laplacian of R by integrating by parts. Anything else? Okay, so this one you may not know, but there's another one you can write down, which is actually a topological invariant, which can only appear, of course, in parity odd theories. In fact, this guy has mainly been absent completely in the literature. I don't know exactly why. And as far as I know, there is no example, okay, of a theory that gives you, a unitary theory that gives rise to this guy. Okay. This guy is the guy that, if you integrate it over a 4 manifold, gives you the signature invariant. So there are essentially 2 basic invariants in a 4 manifold, the Euler invariant and the signature invariant. And this is the signature invariant. Okay, so now we have this laundry list. I will use a more convenient basis of these 3 guys and define, so I'm going to use a basis that's going to be R squared. And now I'm going to take 2 different linear combinations of these guys that will be useful in our analysis of the Weisel-Milne condition. So I'll define the other topological invariant, E4. This is the Euler density. So this is some particular linear combination. Okay, I'm going to write it down. Okay. And then there is a combination of the Weil tensor square. The Weil tensor is an important tensor because it's the tensor that measures conformal flatness of a manifold. Okay, I don't know if you've seen this in GR, but the statement of the Weil tensor is that if the Weil tensor vanishes, even only if the metric is conformal to flat. Okay. So there's another combination of Weil squares that you can write in terms of Riemann, Ricci, and R squared. Oh, I think I copied. Okay, I copied the wrong line. Give us 4. Give us. So this is minus 2R mu no, plus a third R squared. Okay. So that means that the most general anomaly. Again, I'm going to cherry pick coefficients. Okay. Okay. Let's do it like that, so everything is visible. So the most general anomaly so far is this. So d for x, root g, sigma x. So I'm going to put the right factors to make other things simpler. So this is going to be the Wild square part. This is going to be the Euler part. Notice what I did is here, just choose a basis of the first 3 guys, which is involves Wild square, Euler, and then R square. Then I can have the box R1, and then I can have the second invariant, which I'm going to call, just not to write this mess again, S. Minus 1 over 64 pi square S. Okay? S4. Okay, but now we're not done yet, right? We have to impose on this gadget the Wells-Domino condition. Again, it's just a statement that the anomaly should represent the Wild algebra. Okay. And now again, knowing the transformation laws of Wild, under Wild transformation that you can read in a GR book, one thing that you discover is that everyone except this guy passes the Wells-Domino condition. So that means that we have to eliminate this guy, because it's not a good term for the anomaly, because it violates the Wells-Domino condition, which is a very physical condition that if you do two transformations, you should get back to realize the algebra. Okay, so right now it seems like we have 4 anomalies, so we went from 1 to 4. But actually, there's another piece of physics that's very important that I have to tell you, and this is true in general for field theory, even though that's not usually how you learn it in field theory. But another important thing to say is this. So in order to get this, we have to regulate the theory, okay? So when you regulate the theory, you have to choose a certain regularization scheme. Means? Okay? Now you can ask, how to parameterize the difference between 2 regularization schemes, okay? And the way you parameterize the difference between 2 regularization schemes is by writing down all possible, again, it's a regularization, it's something that's happening in ultraviolet, is by writing down all possible local counter terms that have dimension smaller or equal than d. Okay, for this particular case, since we're removing, anyway, in this case, all that matters is that it's dimension d. Okay, so 2 regularizations schemes differ by a local counter term of dimension equals d, okay, which in this case is 4. Okay. Therefore, physically, if there's a, of course, we're interested in physics in observables that are universal, that do not depend on some crap that you did in the ultraviolet. We only care about the things that are really truly physical, and therefore things that can be accounted by just a choice of a different counter term, we don't care about. This is unphysical. It has no physical information. So now the observation I want to make is that if you write down the following counter term, d for x, the square root of g r squared. So this has all the properties. So I have some regulator. Imagine I have my regulator, and now I just want to change it because I feel like it, and I add this extra term in my functional integral. Now the point is that if I make a Wild transformation of this counter term, what happens is that you get precisely sigma box R. Okay? So what this means is that this anomaly, even though it passes all the consistency conditions, is scheme dependent because it can be accounted by a local counter term and therefore is not unambiguous and not unphysical. Okay? So I can eliminate this by saying that this is scheme dependent. Is the logic semi-clear at least? Yes? Well, you know that, but you're not the one that should be nodding. Yeah, okay. Is the logic clear? Okay. And you can convince it yourself. So if you, even in field theory, like 101, if you do dimensional regularization or MS or MS bar, you can convince yourself that the difference between the two is given by a local counter term.
But you can't compare like two vastly different schemes of image.
You can. That's why I said more generally,
I see. So
dimension is smaller than this. Imagine you do brutal cutoff and dim rec. Brutal cutoff will have ultraviolet, So dimension regularization only has logarithmic divergences, or 1 over epsilon poles, while brutal power UV cutoff will have power law divergences. And then the difference between these two is given by counter terms that have dimension D and smaller. So this statement is very general. It allows any two regularization schemes. The one I told you is kind of boring. MS bar. Who cares? I mean, it's. But these two are very different, right? Cutoff and dim rec, for example. And this number, for example, again, you can compute. Originally, it was done by absolutely brute force doing hit kernel method. And just to give you a sense, for example, for a scalar field, AS is 1 over 360, CS equals 1 over 120. And you can ask, what am I not telling you the number for? Oh, here there should be a number, E. So this is the new anomaly, okay? So the anomaly are A, C, and E. And what I can tell you that's kind of interesting, I actually didn't know until I started preparing for this lecture, more essentially, is that, first of all, almost all the literature doesn't have this term. I don't know why. I think the reason is because it's parity odd, okay? But it definitely satisfies all the conditions. And the point is that if you look at all the typical theories that people study, like using hit kernels, the scalar field, fermion, and so on, all these theories have E equals 0, okay? And in fact, as far as I know, there is no example of a consistent unitary theory that would give you E different from 0. Okay? But that doesn't mean that it doesn't exist. And it could be, the problem is that people usually compute these things in a weakly coupled theory. So you do some perturbation theory, and in that theory you get 0, but conformal anomalies, unlike chiral anomalies, can receive contributions to at any loop order or non-perturbatively. So you could have a strongly coupled conformal field theory that, of course, you cannot study using Feynman diagrams in the usual way. But this is crazy. Come on. Dalimil, can you do something about this? Can you ask? I mean, I don't know.
I can try.
I mean, I have enough.
Okay, I'll see what I can do first.
How make is this?
Sorry? No, but.
This rest of the lecture.
Just one doubt. That thing, if I smear with the root G is scalar, but in and of itself, it's like
Yeah, so here I was not careful. So here,
yeah,
this shouldn't have the square root of G. This has the square root of G in it through the,
otherwise it won't be scalar. So
Yeah.
is that probably why?
No, I was not being careful. I should.
Right.
This guy is definitely a scalar, okay? Sigma.
Yeah, I mean, it's right.
So it's definitely allowed.
No, but that's what I'm saying.
Yeah.
The rest of them are all densities.
I don't think I'll be able to do anything. There's that's the format which already started, and they don't seem like they're going to finish. So what we can do, we can move to a different room, which is
Well, actually, it's being recorded. So let's see. So, well, can you hear? I mean, I'll try to concentrate. I'm not sure. If I start moving, then it's... it's like Texas. Okay, sorry, I'll try to concentrate, otherwise it will be...
So if I had a counter term of D dimension, that could be marginal, right?
Yeah, this one is marginal, right?
So it could be marginally irrelevant, and I don't want...
No, but this is a background field. It doesn't change this dimension, right?
So, let's question about it. So, E can only be this number. E can only be non-zero if the CFT is partial. Right?
Yes.
If it's partial, value is partial. So, are there any
Yes.
non-interesting CFTs in
Yes.
which value is partial?
Yes. But yes. And I think it's an interesting problem to study whether E is... Some of them can be strongly coupled. So you cannot just do Feynman diagrams. You have to use other methods to study them.
But has anybody tried to compute E in a parity non-preserving four-dimensional CFT?
Yeah, so the thing I've seen, actually, this was only computed last year. So what people did is take a wild fermion. Just a stupid free wild fermion. Okay, I should show me respect. Okay, some free fermion. And you can compute E. The strange thing that happens is that what you get is that E is imaginary. So in some sense, it's some kind of violation of unitarity, right? Because now all of a sudden the stress tensor. Okay, one thing I should say from here is that this implies a relation for the stress tensor, right? It tells you that T mu mu. So if you have an eye here, in some sense, you made the energy imaginary. So one has to think what this really means, okay? So the only example I know is this one. You take a chiral fermion, and you get some E, but it's imaginary. But now I can imagine, and this is just computed using a heat kernel, a free field. Okay, just computing the determinant of the Dirac operator or the Weil operator in the background metric, and extracting the heat kernel coefficient, the width coefficient. But you can imagine now I can give you a strongly coupled CFT that is parity odd. There is no guarantee, at least not known, as far as I know, whether such an E, you can write an E that would give rise to a unitary theory, or a unitary energy, or a real energy.
So why can't the counter term be more than D dimension?
Sorry?
Why can't I add a counter term?
Okay, because if you do, the physical way to think about it is that this will be suppressed by powers of a cutoff. And in the continuum limit, when you remove the cutoff, it will go to zero. They're irrelevant. So, you know what I mean by that?
But that seems to be growing in the...
I'm saying that when you renormalize, one way to think about it is that you put a cutoff, you add counter terms that depend on the cutoff, and then you take the cutoff to infinity, right? The terms that you're talking about will be suppressed by 1 over the cutoff. So when I take the cutoff to infinity, they don't survive in the continuum limit. Okay, so now the point is that, again, taking functional derivatives of this guy, this becomes harder in 4 dimensions because there are stupid indices floating around and so on. C enters the 2-point function of T mu nu in flat space. So now it's in flat space. Okay, and A enters not the 2-point function, but the 3-point function. And actually, as far as I know, people have not analyzed whether E enters some 3-point function of T mu nu. That's an interesting problem.
Is it only A which enters the 3-point function, or also C?
I think both A and C. There are 3 different tensor structures in the parity even sector, and I think C enters also in there. But okay, we already know C from the 2-point function, so. Okay, so now you can ask the same question we asked before, so this is great. Why do I care about this? So now you can ask the question whether, again, there's some quantity here, like here, that will decrease along the RG flow. So can you guess if what of the three central charges will have this property? Why?
Well,
why would this work? I imagine since it covariant like scales with rescaling, it shouldn't do anything, but A probably.
Okay, it's A, yes.
Yeah.
No, the reason it's tricky is that for some strange reason, they have obnoxious notation in 4 dimensions. The one that survives is A, not C. But anyway, that.
Right, no, but logically, since the wild tensor in and of itself like scales covariantly.
Well, it doesn't. It's
exactly.
It doesn't scale. Yeah.
Since it doesn't scale, then the one that would be sensitive to rescaling, it also has to satisfy the consistency condition.
No, but this already is all of these already satisfied,
exactly.
right? Yeah.
So since it does, then the one that will be sensitive to it will probably be A. Like if you
So it's A. So it's A. Yeah. So, but this was called for many years. There was a Cardi conjecture that AUV, I guess, in one of these RG flows is bigger than AIR, and actually it was only recently proven. So I will not go through the proof here, even though I recommend that you look at the paper. It's quite readable, and I think, well, I hope that at least with what I told you during the course, at least you would be able to follow most of it. Kumar. Swimmer. And it's in HepTH. Okay. So essentially what they've done is give a construction of a quantity, just like capital C in 2 dimensions, that has the property that decreases along energy flow, and at the asymptotic regimes reduces to the A anomaly. Okay. Okay, so now you can ask what we're trying to see whether, of course, we're interested in this kind of RG flows in any dimension, not only in even dimensions, right? So you can try to ask what could possibly be the object that would have this property in odd dimensions. And a useful thing to do is to try to see whether we can think of C in 2 dimensions and 4 in 2 dimensions in a unified way. Okay, and this will give us it will lead us to the answer or conjecture, depends how precise you want to make the claims. So something that you can immediately see, well, okay, not immediately, but you can try to study the theory in geometries that pick out precisely the coefficients that have this monotonic behavior. So in 2 dimensions, just to remind you, it was something like 20 R. Okay. So the geometry that has the property that vanishes where the Well tensor vanishes and S4 vanishes, but this guy is also the Euler density in 2 dimensions. It's exactly the sphere. The sphere has the property that if you integrate R over it is non-zero, and this guy is also non-zero. Okay? It vanishes because a sphere is conformally flat, and the signature vanishes because there are no 2 cycles in some sense in a force sphere. Okay? So spheres kind of very nicely isolate the quantity that we want. So what you can imagine is the following: you take your CFT, you can do it in these dimensions, and conformally map your CFT in the plane doing a wild transformation. You can formally map it to a sphere of radius r. Okay, this you can do. Now, if the theory was really conformal invariant, there was no conformal anomaly, the partition function on the sphere would not depend on the radius of the sphere, because that's what it means that it's conformal invariant. It doesn't depend on the scale. But the fact that you have a conformal anomaly precisely tells you that it depends on the radius of the sphere, but in a very particular way. Okay. So what you can do, so I don't know how much detail I should give you about this. I think, okay. What you can do is essentially the following. Just ask, how does the partition function of a conformal field theory on the sphere change as I change the log of the radius, okay? Or one way of saying it is I take my metric. So let me use these convenient coordinates. So this is the metric on a sphere of radius r. This is true in any dimension. And I rescale the radius of the sphere by a little bit. And now you can ask, what happened to the partition function? An overall rescaling, a rescaling of the radius is equivalent to rescaling the metric, okay? So that means that this guy is going to be proportional to the integral of T mu mu, okay? Because remember what we're using here is that T mu nu is 2 times the variation of the action with respect to delta G mu nu of x root G, okay? So now what I'm doing essentially is just, another way of saying it is this, that delta Z is dx T mu nu delta G mu nu, right? Now, I make a deformation where I just rescale the radius. This is proportional, delta G mu nu for the sphere. If I just rescale R, okay. I didn't want to give details and I end up doing the details, but okay, that's life. Are people happy with this formula? Okay? So that means that if I look at this guy, I have that delta Z is delta log R times the integral of square root of G P mu mu, right? But now this guy is precisely just the anomaly. Of course, this is integrated over the d-dimensional sphere. So now I plug in the right-hand side of the anomaly, and only the Euler part survives. What you get is, just to use common notation, I'll say C times d log of R. So what this tells you is that Z has an anomalous scaling, with the radius that goes like R to the C. Again, C equals, okay, in D equals 2, and C equals A in 40. Okay? So there is a quantity that you can compute. Is you take the conformal field theory, you conformally map it to the sphere and compute the sphere partition function. You can prove, I will not do it here, that the unambiguous part of the partition function is the only physical quantity in the sphere partition function is precisely the exponent in the coefficient of the radius. Okay? So this allows you to read off C in a given conformal field theory. Okay? So now you can ask, what if I tried this in odd dimension? I can certainly study the partition function of conformal field fields in odd dimensions. By the way, all these are pretty recent developments in the last few years. Well, you can see, for example, this was 2011 or 12, whatever. The basic point is, so at least conjecturally, so now you can ask, what is there a quantity in the odd that decreases under RG flow? And it turns out that the answer is yes, and it's captured precisely by the same quantity that captured the relevant central charges in even dimensions, which is the sphere partition function. So you can take your favorite CFT and put it on a sphere and compute the sphere partition function and define some kind of free energy. Okay? This defines a kind of free energy. And the thing that you can prove, again, doing a essentially what you can prove is that this guy, of course, in general will have some divergent pieces, but it will have some finite piece, okay? So the finite piece of F is the quantity. This is the conjecture, at least. I think it, with some assumptions it has been proven in 3 dimensions, is the RG, the monotonic RG quantity that we were looking for. Okay, so again, in this case, what will happen is that you have F UV will be greater than F by R.
So is that allowed to depend on the radius of the sphere?
No, precisely, because
There is no anomaly.
yes. So now you read it from a different place, but you read it from the partition function of the sphere. So it doesn't depend on the radius, but it's there. So for example, in 3 dimensions, okay. Sorry?
It has nothing to do with the radius of the sphere per se, because it goes back to the logic that which invariant is sensitive to scaling transformations.
No, but for example, here I'm saying that to extract the central charge, you look at the R dependence of the partition function. Here, there is no R dependence, but nevertheless, it defines a scheme-independent quantity that has this property of monotonicity. And the last thing I will just say, just at the level of buzzwords, is you can ask, clearly the partition function of spheres in any dimension seems to be an important object. You can ask, what is its physical meaning? Can we ascribe to this an intrinsic physical meaning? And the answer is yes. I'll just tell you what it is. I'll tell you the buzzword, essentially, so that you keep it in the back of your mind. And you will hear them again for sure. So essentially what I want to say is that, let me start with a different problem that looks completely different. And I will not show you, but believe me that after a few steps, which are rather elementary, you can show that the following statement is true. So imagine first that you study a conformal field theory in Minkowski space. This is true in any dimension, no? Okay, and I look at a fixed time slice. Okay? In this fixed time slice, I look at the d minus 2-dimensional sphere, okay? Which I call this region A and region B. Okay, so there is a region which is a sphere. The region inside the sphere is region A. The region outside the sphere is region B. Now there is something, so this is the part that I don't want to get into the details, but there is something that you can always define. If I give you the vacuum of the conformal field theory, which is conformal invariant, actually you can do it for any pure state, actually for any state for that matter. You can define a density matrix. Okay, let me not get into so many details. You can define what's called the entanglement entropy. Have you heard this word before? Mm-hmm. Okay, so between region A and region B, okay? So there is some entropy that depends on some density matrix that you construct from the state that you choose. So in this case, we're choosing the conformal invariant state. And essentially, the statement is that after doing a few conformal transformations, gymnastics, you can essentially map this problem of computing. Essentially, this maps to the partition function to the thermal partition function of the Sitter space at temperature given by the radius. Okay, so here this guy has some radius r, and then you compute the partition function of the Sitter space at temperature r in the usual way we compute thermal partition functions by doing the Euclidean functional integral with one coordinate which is periodically identified. And you end up precisely with the computation of the SD partition function. Okay. So the statement is that the SD partition function, the scheme-independent part of the sphere partition function, computes the entanglement entropy in the Lorentzian theory for a d minus 2-dimensional sphere with the rest. Okay. So that's kind of a nice physical unifying picture in any dimension of what the partition function computes. Yes, you have a question, I can see. Yes.
So in the dimensions where we know that this quantity depends on r, is the radius of the sphere on the right correlated with the radius of the sphere on the left?
Yes.
it is the same.
Yes.
The radii is.
Right, right. Okay, so now they finally stopped. So I guess I have to stop too.